research that I'm doing right now is pretty much exactly in the field that I originally got interested in as a high school student. So I got really fascinated about relativity and how mass and energy converge and how all these fancy relativistic effects when masses are traveling at a fraction the speed of light and all the phenomena that go with it. And so I became a relativist in some sense, and I'm doing relativistic astrophysics. We look at neutron stars and black holes where gravity and relativistic effects are very important and in fact the dominant sort of agent in the system. And so from that first high school experience until now, it's kind of just pursuing that path and that fascination that got me hooked up with physics in the first place. My name is Daniel Siegel. I'm an assistant professor here at the Department of Physics at the University of Guelph. And I'm also jointly appointed with the Perimeter Institute for Theoretical Physics in Waterloo, which is just a 30-minute drive from here. So I went to school in Germany, and you might hear that from my accent. I studied there at the University of Freiburg in the southwest of Germany. I spent 3 years doing my PhD at the Max Planck Institute in near Berlin in Potsdam. Then I moved over as a NASA Einstein Fellow, as a postdoctoral fellow to Columbia University in New York City. Where I spent roughly 3.5 years before coming here. So I'm an astrophysicist, so I'm interested in essentially the cosmos and how it works. Specifically, what fascinates me is are very peculiar objects called black holes and neutron stars. So what, for example, happens if you collide two black holes or two neutron stars, and what kind of cosmic astrophysical phenomena these collisions or these interactions give rise to. This has actually formed a completely new field in physics that's becoming a big mainstream field in physics called gravitational wave astronomy, or also called multi-messenger astronomy, where for the first time now we're actually able to discover these sources to detect signals from such cosmic collisions far away out there in the cosmos for the first time using gravitational wave interferometers, gravitational wave detectors. So we detect little ripples in space-time that these objects cause as they gravitationally interact during the collision. We can also see light, electromagnetic light being emitted from these sources as they interact, which we call a kilonova or a short gamma ray burst. These are extremely energetic events. In fact, the most energetic events that we know of in the universe. So what we kind of do in my sort of theoretical field of astrophysics is we kind of use these huge machines, these supercomputers, essentially to replace a laboratory for in other fields of physics. So essentially we try to perform numerical experiments on these big supercomputers to see, for example, how two neutron stars or how two black holes interact with each other. It's very interesting that in astronomy and astrophysics we actually don't have a lab where we can do controlled experiments, and so so the empirical part of our science is essentially completely relies on observations. So we have to be very lucky to see something interesting that we hope to learn something from, and so as theorists. We try to really use these supercomputers to replace the experiments and to actually do controlled experiments in a numerical sense to see how such collisions, for example, occur out there in the universe. So you can think of it as a little bit in between of a pure theorist that just uses pen and paper calculations and a sort of experimentalist that does controlled experiments in a lab. So yeah, I do work with undergrad students, essentially through all the different career stages of an academic career, all the way from say second, third year undergrads up to postdocs who would then move on to faculty position elsewhere. The way to think about this is a undergraduate student in like the third or fourth year or so would join our group and would be sort of embedded in this larger group of students and postdocs at these different career stages, and so they will connect and work together with sort of more experienced members of our group. So typically there's lots of ways to get scientifically involved, for example, to analyze and visualize simulations. For example, some of the big supercomputer simulations, we do visualize them in a way that's intuitive to us humans and to get some intuitive understanding about what actually physically happens in these in these physical systems. Other projects could involve, for example, doing simple calculations, small calculations to make some predictions for new phenomena that we might expect from such systems. So there's sort of more theoretical pen and paper, but also sort of more computing-based, visualization-based projects that can be thought of. What's really fascinating about the department is that we have a really strong group in this field of gravity, of relativistic astrophysics and gravitation, with multiple faculty working in that area. And that also nicely connects to nuclear physics in the department. So one of my basic and main sort of research questions that I try to answer is, how does the universe actually create heavy elements? And so it turns out that these very relativistic objects like neutron stars and black holes actually give rise to these heavy elements. And so there's a nice connection between essentially the group of gravitation and relativity and nuclear physics and nuclear astrophysics. I think one of the most fascinating moments in the sort of recent history of the field, so in the last couple of years, was essentially the first detection of the collision of two neutron stars that happened far away and a long time ago. And so that was the first really merger of two neutron stars, collision of two neutron stars that we detected with gravitational waves, but also with light. And it just so happened that we had done some computer simulations just before the event happened, and we predicted that based on these theoretical calculations on supercomputers, that these sources should emit, sort of give rise to ejection of masses and create heavy elements in a certain specific way. That turned out to be a perfect model for the actual emission that was detected, that was observed in this event. And so it was just a fantastic moment to see the power of theoretical calculations and of theoretical prediction to come true, and to see that the universe can actually behave in such a way or in a similar way. It's just very fascinating and provides a lot of enthusiasm to see how theoretical calculations can actually fairly precisely predict phenomena that can be observed out there in the universe, and that in something as complicated as the merger of two neutron stars somewhere out there in the universe can actually behave like something that you model on a supercomputer. And just to see these predictions that just happened, to be available a few weeks to months prior to this event, then actually coming true, is just a fantastic moment.